In this online lecture, we're going to discuss more types of fragmentation for molecules, and we're going to go a little bit further than what we did before in a previous online lecture. And what we're going to learn here is that number one, there are three general types of fragmentation: heterolytic cleavage, homolytic cleavage, which is sometimes called alpha cleavage, and McLafferty rearrangement. We're also going to see that number two, halogens, ethers, and alcohols can cleave heterolytically and homolytically. And number three, we're going to see alcohols can fragment by loss of water. And the last type of fragmentation we'll see, number four, ketones can fragment homolytically and via what's called McLafferty rearrangement. So let's start here. As discussed, we have different types of fragmentation. We're going to look at each one, and we're going to see there's heterolytic, there's homolytic, which is also alpha cleavage, and then there's McLafferty rearrangement. Let's look at heterolytic cleavage first, right here. Notice what we have here. We have an alkyl halide. And what we've discussed before in a previous online lecture is that when you stick this molecule in the mass spec, it is possible that the electron beam could actually dislodge this electron right here on the Br. If that does happen, we end up with this species right here. And if this is the only thing that happens to this molecule, then this particular species will give rise to the molecular ion peak. But what we're learning here is that something else could possibly happen. Notice, remember, we got the positive charge right here, which means it has the ability to attract electrons. And that's exactly what happens here. It attracts the electrons in the bond here to jump up on top of that positive charge. If that happens, it's called heterolytic cleavage, meaning that the bond is breaking heterolytically. Now, let's look at the result of that move right here. You would end up with this structure and this Br fragment right here. So, think about this. If this happens in the mass spec, then it's this structure right here that's going to go through and be detected by the mass spec. So we should expect to see a peak at 43. And sure enough, if you look at the mass spec of this molecule, we'll notice we got the 43 peak right here. And of course, notice you got the molecular ion peak, 122. And of course, you got the M+2 peak due to the fact that this molecule has a Br in it at the 124. So what we're learning here is that alkyl halides can cleave heterolytically, which is technically another way to learn how these molecules crumble. But it's not only halogens that can cleave this way, alcohols can do this as well. And it's the same kind of dynamics here, and that's what we want to pay attention to. Notice it's not very different. Watch what happens here. Again, we stick this alcohol in the mass spec, and let's say the electron beam just so happens to dislodge this electron right here. We would get this as a result. And again, if this molecule were to go through the mass spec just like this, we'd get the molecular ion peak. But because this positive charge right here is on the oxygen, it is possible that the electrons in this bond could jump up on top of this oxygen, and that would be a heterolytic cleavage. And the result of this movement would be something that looks like this. And again, just like we saw before, it's really this fragment that has the charge, which will be detected by the mass spec. So we should also see a peak at 43 for this alcohol. Now, notice you're going to see this same type of cleavage with ethers as well. Again, watch what happens here. Let's say in the mass spec, the electron beam happens to dislodge this electron right here on the oxygen. We would end up with this species right here. And we can get the same type of heterolytic cleavage, meaning the electrons right here could jump up on top of that oxygen. But think about this for a second. If that did happen, that would make this carbon right here become a carbocation. And what type of carbocation would that be? Well, of course, it'd be a primary carbocation. But with ethers, you technically have a choice here. Instead of this bond heterolytically cleaving, we can say that this bond heterolytically cleaves. If this happens, notice this carbon right here will become a carbocation, and he will therefore become a secondary carbocation. Since that's more stable, then it's more likely that the bond on the right-hand side of the oxygen will heterolytically cleave, which means we'd end up with these two structures right here as a result. And of course, it's this guy right here, the one with the charge, that's going to be detected by the mass spec, so we should expect to see a peak at 43 for this ether. Now careful, we're not saying that the bond on the left side of the oxygen will not heterolytically cleave. It's just the bond on the right of the oxygen is more favored to cleave. Now let's look at the second type of cleavage here. Instead of heterolytic cleavage, now we have something called homolytic cleavage, which again is also technically called alpha cleavage. It's good to know this because alpha cleavage is going to help us with our quick product method here, which we'll learn a little bit later. So to learn homolytic cleavage here, it all kind of starts out the same way. We stick this molecule in the mass spec, the electron beam just happens to dislodge one of these electrons right here. We end up with this thing right here as a result. And let's talk nomenclature for a second here. It's always going to be this way. The carbon that is directly attached to the halogen, he is considered the alpha carbon. And remember, we learned before that it's possible that you could have heterolytic cleavage at this point. But what we're looking at here is simply just another possibility. Again, another way that the cookie can crumble. Let's first look at the electron movement of alpha cleavage. It actually looks like this right here. Let's focus on what's happening here. Notice right here, this bond, if the two electrons are leaving, that means this bond is not going to exist anymore. That bond is being broken, and notice that bond is connected to the alpha carbon, which is how this type of cleavage gets its name, alpha cleavage. But notice what's happening over here on the other side. Two electrons are coming down together. That's going to create a new bond between the alpha carbon and the Br. In fact, let's look at the results right here of this movement. Take a few minutes and make sure you see where these electrons went and how we got our products here. Now, the next thing we should look at is which one of these fragments is going to be detected by the mass spec. Well, of course, it's always the one that has the charge, this one right here. So for this molecule, we can expect to see a peak at 93. In fact, let's look at the mass spec of this molecule. Notice there it is, the peak at 93, and that's due to this fragment right here. But remember, we learned in a previous online lecture that Br comes in two isotopes, Br79 and Br81, which means it's also possible to get a peak at 95 due to this fragment right here. And notice our relative heights here. They would be the same because the relative abundance of Br79 and 81 are roughly 50-50. Now, let's pause a second here. You might be slightly getting overwhelmed by all these different fragmentations. Well, just hang on for a second. I'm going to keep explaining some more different ways that molecules can fragment, and then I'm going to show you specifically how you would apply all this type of fragmentation on a typical test question. So for now, just sit back and at least understand what's happening here. I'll pull it all together, I promise, in a few minutes. So let's look at another type of homolytic cleavage, but this time with ethers. Again, we start out in the same fashion here. The electron beam knocks out this electron right here, and we end up with this thing here as a result. And again, we saw before that this can heterolytically cleave this way, but we're focusing now on alpha cleavage. And notice this carbon right here would be considered our alpha. This is how we locate the alpha carbon on an ether. It's always the carbon that's directly connected to the oxygen. And what I want to show you here is the electron movement of the cleavage is identical to what we saw before. It looks something like this. Notice again what's happening here. The bond connecting the alpha carbon right here is going to be broken, and there's going to be a new double bond forming between the carbon and the oxygen right here. Let's look at this resulting move right here. You'd end up with these two structures. Notice the fragment on the right, the oxygen there, has a positive formal charge, which means this is the structure that's going to be detected by the mass spec. so we should expect to see a peak at 73. But what I want to show you here is that when it comes to ethers, you can technically alpha cleave on either side of the oxygen. So let me show you that. Let's start over here. Again, we stick it in the mass spec, the electron beam dislodges this electron right here, and we're back to this original structure here. But notice, let's look on the right-hand side of this oxygen. This would be the alpha carbon here. And the electron movement here for alpha cleavage would look something like this. Notice the similarities. One of the bonds to the alpha carbon right here is being cleaved, and we're getting a new double bond being formed between this oxygen and the alpha carbon. And let's look at our results right here. Make sure you see who went where. This methyl right here in green would be this methyl right here. And notice, since he's neutral, he wouldn't be detected in the mass spec. Of course, it is this molecule right here that would be detected, so we should expect to see a peak at 87. Now, let's pause for a second here and try a sample problem. Again, this seems like a lot of information, but let me show you how you're going to pull it all together. Here's a typical problem here. It says, which molecule below would exhibit MZ peaks at 43, 57, 87, 101, and 116? And notice we have three molecules here: propyl chloride, isopropyl bromide, and S-butyl isopropyl ether. Think about our plan of attack here. We want to look at each one of these molecules and look at all the possible ways that the molecule can fragment. And then we're going to look at each fragment and see how much it weighs and see if we can match up to the numbers 43, 57, 87, 101, and 116. This is the necessary skill in this section. So let me show you how to do this. Let's start with the propyl chloride right here. And where we should start is with just the simple molecular ion peaks. Remember, we can assume that one of the electrons on the chlorine could be dislodged, which would give rise to this structure right here, which means this should peak at 78. But remember, we also learned in a previous online lecture that chlorine comes in two different isotopes, so it's possible to get this fragment as well, which means we should see a peak at 80, and this of course would be the M+2 peak. Now, right away, this doesn't look like it might be the answer, but what's more important right now is let's just keep going to learn how to break up a molecule and to do it quickly. So that takes care of our molecular ion peaks, but remember, this is an alkyl halide, which means we should know that these can break up heterolytically. And it doesn't take much to simply do this in your head. You know that in a heterolytic cleavage, all you're doing effectively is breaking this bond right here and leaving behind, therefore, this fragment. And this fragment happens to weigh 43 grams per mole. So that would take care of the heterolytic cleavage. But remember, we also know that alkyl halides can also alpha cleave, which means we want to quickly alpha cleave this molecule. Now, to do that, let's develop a quick product method here. Let's pause for a second. How do we quickly alpha cleave on an exam? Well, let's remind ourselves what exactly happens. Remember, here's the alpha carbon right here, and this is the electron movement right here for alpha cleavage. And remember, we said it's this bond right here, and think about it. That's the bond on the other side of the alpha carbon. And when I say other side, meaning the one not connected to the halogen. It is that bond that's always going to be broken, and it is always this bond right here that's going to turn into a double bond. Or in other words, the alpha carbon is in the end going to be doubly bonded to the halogen. Because remember, this is the result that we get. So here's how it's going to work then. To quickly do this, notice you'll locate the alpha carbon right here. And remember, it's always the bond that follows. This one right here is going to be severed, which means you're going to get this as a fragment on this side. And remember, it's the other side right here is going to be the other fragment. And you have to remember to double bond that alpha carbon to the halogen like this. And we're always going to get this on the other side, on the blue side fragment here. He's always going to become a radical. So this is how we alpha cleave without having to draw all those mechanistic steps. So let's go back to our problem here. Notice we want to quickly alpha cleave. Let's apply what we just learned here. Again, remember we start with locating the alpha carbon right here, and we know that the bond following it, this one right here, is the one that's going to be cleaved, which means on the right side of that cut mark, we're going to have the alpha carbon doubly bonded to the Cl like this. And the left side of that cut mark right there is going to be the radical fragment. However, we know the fragment on the right is going to be the one detected by the mass spec, so we should expect to see a peak at 49. But again, remember we know Cl comes in two different isotopes, so you're not only going to see this fragment, but you're also going to see this type of fragment, which is alpha cleavage if the Cl happens to be Cl37. So we should expect to see a peak at 51. So notice what we did here is we found all the major possible fragments of this molecule. We should expect to see peaks at 78, 80, 43, 49, and 51. Now, obviously, that means this is not the answer because that's not the peaks that we're looking for. But notice how we quickly do this on an exam. So it's kind of like performing surgery on the molecule. We're simply slicing and dicing and seeing what we get. So let's go back to our problem here. We have just ruled out propyl chloride. Let's look at the isopropyl bromide. Here's what he looks like. And again, let's quickly slice and dice this molecule and see what we get. Well, first we should note, what is the weight of our molecular ion peaks? Well, these structures right here would give rise to the molecular ion peaks. We should expect a peak at 121, and we should expect an M+2 peak at 123. Which right there, right off the bat, not looking good for this molecule being our answer. But again, we're learning how to cut up here, so let's keep going. The next thing you should focus on then is, you know, alkyl halides can heterolytically cleave. So again, you're going to quickly on the test just knock this bond out right here. And what's left, of course, is a carbocation. So we should expect to see a peak at 43 due to heterolytic cleavage. And we also know there's another type of cleavage here with alkyl halides, alpha cleavage. So let's do our quick product method. We're going to locate our alpha carbon right here. And notice we're going to make our cut mark, which could be right here, but it could also be on the other side of the alpha carbon as well, or the right-hand side. But notice that wouldn't be any different. So all you have to do is just focus on one right here. And again, remember how we quickly do this. On the left-hand side of this cut mark, this guy right here would become the radical. And on the right-hand side right here, we can expect to see the alpha carbon doubly bonded to the Br. So that results in these structures right here. And remember, it's the structure on the right that has the charge, which will be detected by the detector, and that happens to weigh 107 grams per mole. And again, we know that this is not the only fragment we would get. Again, because Br comes in two isotopes, we can expect to see this fragment as well. So again, no dice here, right? These are the peaks that we expect to see. These are the peaks that we were looking for. Doesn't match up, so that means this can't be our molecule, so we rule him out, which means S-butyl isopropyl ether is probably the one. So we're going to investigate him to make sure. But let me pause for a second here and make a note about an exam in organic chemistry. You might be looking at this and saying, wow, this is a lot of work for one question on a test. But remember, we could have ruled out the first two molecules a long time ago just by simply looking at their molecular ion peaks. So this process can be very fine-tuned and a lot of the steps could be cut out in order for you to get to your answer quickly. And I also want to note that this is going to take some practice. For you to quickly do this, you're going to have to do a lot of these problems to build up that speed. Luckily, there's plenty of these practice problems in your textbooks. So with that, let's do our analysis with this last molecule here. Here's what he happens to look like. This is S-butyl isopropyl ether. And let's begin our analysis with the possible molecular ion peak. It should be this right here, 116. This bodes well. That is one of the peaks that we're looking for. So let's keep track of our progress here. Let's put him up over here. Now let's talk about the types of cleavage we might get. Well, remember, one possible thing that ethers can go through is heterolytic cleavage. So that means we can heterolytically cleave, let's say, the left side. If that happens, you make that cut right there, you're going to end up with this carbocation on the left-hand side. So we should expect to see a peak at 57. But remember, ethers can cleave on either side heterolytically. So we'd want to cut here as well and know that on the right-hand side, we would get this fragment. So we should see a peak at 43. So that takes care of our heterolytic cleavages here. But we also know these molecules go through alpha cleavage as well. But again, we want to do this very quickly. So let's do the same thing we did before. Let's generate the quick product method here on how to alpha cleave an ether immediately. Let's go back here. Remember, what we said was the electron movement looked like this. We located our alpha carbon and the electrons moved in this fashion right here. And again, just like we saw before, it's this bond right here following the alpha carbon that breaks, and this bond is becoming a double bond, which means we end up with this result right here, these two structures. So how are we quickly going to do this then? Again, starting from the beginning, you're going to locate your alpha carbon, and just like before, you're going to make your cut right here. And what you should do is focus on the right-hand side of this first, because remember, that's the side of the molecule that's going to give rise to a peak in the mass spec. So you're looking at this side right here, and remember, you're knowing to take that alpha carbon and make sure it's doubly bonded to the oxygen like this. And again, just like we saw before on the left-hand side, this is the fragment that takes on the radical. So this works every time, and that's how we quickly alpha cleave an ether. So let's go back and try our method here. Again, we locate our alpha carbon right here, which means our cut mark could be right here. And again, you're focusing on the right-hand side here. This is what would be the result on the right-hand side. Notice our alpha carbon is doubly bonded to that oxygen. That fragment happens to weigh 87. And of course, on the left-hand side of this cut mark, we can expect this radical right here. Now, careful, you might be looking at this and saying, why didn't we make the cut above the alpha carbon, therefore removing that methyl? Well, think about it. If we did cleave that methyl, we would end up with a methyl radical. And remember, our radical stability is that tertiaries are more stable than secondary, more stable than primary, more stable than methyl. So cleaving this in the way that you see here that we did would lead to a primary radical. So we're simply saying that this kind of alpha cleavage is going to be favored. However, remember, we can also alpha cleave the other side of this oxygen. So let's look at that. Again, on the right-hand side, we'd locate this as our alpha carbon, and it means that we can cut right here. In this particular case, again, it doesn't matter whether you cut here or you cut above the alpha carbon, you're going to get the same thing. So let's just focus back on this one right here then. Remember, if it does cleave right here, the alpha carbon is going to be doubly bonded to that oxygen. So we quickly generate our fragment right here. And as a side product, we're going to get the radical here, the methyl, which, by the way, would mean that the alpha cleavage on the left-hand side of this ether is more favored than the right-hand side. Again, because the right-hand side of alpha cleavage for this ether leaves behind a methyl radical. But nonetheless, it is possible, and the fragment that we would get here happens to weigh 101 grams per mole. And notice, look at all of our fragments here. Notice these values. They do match these values right here in the problem. So there it is. We found our molecule. He is the one that would give those particular peaks in the mass spec.